Welcome to my video lecture based on electric circuit theory. My paper code is PCE 301 and this total syllabus content is based on Macau curriculum. In a previous lecture, we have discussed about different modules of electric circuit theory, and in my previous module, we have just completed about graph theory. In this lecture, we will start with a new module which is magnetically coupled circuit. And in this lecture, we will just introduce what is magnetically coupled circuit, and we will just quickly describe on how the circuit can be actually coupled magnetically, and those things we will discuss here. Mainly, coupling means it can be self-induced EMF or self-inductance and mutual inductance. It can be coupled magnetically between two different windings, or it can be coupled by its own magnetic field. So that concept we will briefly describe here. Myself, Umun Banerjee, Assistant Professor of Electrical Engineering Department, Dr. Subichanishu, Institute of Technology and Sports Complex. Previously, it was known as Dr. Subichanishu Degree Engineering College, and this institute is under GISB. So, let us start with the topic, that is Introduction to Magnetically Coupled Circuit. So, the circuit we have considered so far may be termed as conductively coupled in the sense that one coil affects the adjacent coil by current conduction. But when two or more coils are very close to each other, then the current in one coil will affect the EMF induced in the other coils. And these coils are just said to be mutually coupled or magnetically coupled coils. In this chapter, we will first discuss the concept of magnetical coupling and the conventions required to write Thevenin equations with product polarities. Then we will learn the theoretical aspects of transformer and field circuits. That means, what is basically magnetically coupling? Here we are highlighting that if two coils are just adjacent with each other, and we have given supply to one coil, and then a self-induced EMF will be produced in the coil where we have given the supply. Let us we have given the supply in this coil, and the EMF will be induced here. Now, due to that EMF induction, a flux will be start going, and this flux will link the adjacent coil. And due to this flux linking, an EMF will be induced in the adjacent coil, and that is called mutual induction. It is called mutual induction, and that EMF is known as mutually induced EMF. So, here two things I have already highlighted. One is self-induction. Due to the self-induction, the EMF is induced in the first coil. Now, what is self-induction? That we will now. Consider a coil consisting of n number of turns. Let us, this number of turns, this one is n. These turns are number of turns are n. And carrying current I. I amount of current is going here. Okay. In the counterclockwise direction, as shown in the figure, if the current is steady, then the magnetic flux through the loop will remain constant. However, suppose the current I changes with time, then according to Faraday's law, an induced EMF will be arise to oppose the change, and the induced current will flow clockwise if di by dt lesser than 0, and counterclockwise if di by dt greater than 0. The property of the loop in which its own magnetic field opposes any change in the current is called self-induction. It is called self-inductance. That means what's happened? When an alternating current, AC current, is flowing through the coil, due to the nature of this current, by itself it is time varying in nature. Okay. Due to this time variation in nature, that means whatever amount of current is flowing, that is changes with time. That means dIdt changes with time. So due to that changing, according to Faraday's law, we know that EMF, whenever the flux linkages are changing, and EMF is induced. So due to that, EMF will be induced in that coil, and that EMF is due to self-induction. And this one is known as self-inductance. And the EMF generated is also known as self-induced EMF or back EMF, which we denote at EL. All the current loop exhibit this property. In particular, an inductor is a circuit element which has large self-inductance, and mathematically the self-induced EMF can be written as EL equals to minus N d phi b dt, where N is the number of turns and phi is the flux, and this is the time variation. So we can write it equals to minus N ddt of integration double integration v dA, and is related to self-inductance L. So we can write it EL equals to minus L di dt. Now from the two expression we can write that L equals to N phi b by I. Physically, the inductance L is measured by an inductor's resistance to change of the current. The larger value of L, the lower current of change of current. And in short, we can write L equal the internal resistive property of an inductor, that is inductive reactance. And generally, we are expressing that inductive reactance in the term of XL, that is omega L. So that is the inductive reactance offered by an inductor. Now, coupled inductor. Coupled means when two inductors are just nearly adjacent to each other, then what will be the effect of the inductor among each other? That is the coupling. When the magnetic flux produced by an inductor links another inductor, these inductors are said to be coupled. Coupling is often undesired, but in many cases this coupling is intentional and is the basis of the transformer. When inductors are coupled, there exists a mutual inductance that relates the current in one inductor to the flux linkage in the other inductor. Thus, there are three inductances defined as coupled inductor. So, let us consider L11, the self-inductance of inductor 1. This one. Then L22, the self-inductance of inductor 2. Then L12 is equals to L21, that is the mutual inductance associated with both inductors. When either side of the transformer is tuned circuit, the amount of mutual inductance between the two windings determines the shape of frequency response curve. Although no boundaries are defined, this is often referred to as loose, critical, or overcoupling. When two tuned circuits are loosely coupled through mutual inductance, the bandwidth will be narrow. As the amount of mutual inductances increases, the bandwidth continues to grow. When the mutual inductance is increased beyond a critical point, the peak in the response curve begins to drop, and the center frequency will be attained more strongly than the direct side bands. This is known as overcoupling. So, that coupled inductors, two adjacent inductors are nearby placed, and the self-inductance of one coil is L11 and another coil is L22, and the mutual inductance associated with the both inductors are L12 equals to L21. Okay, that is the term we are actually expressing. Now, mutual inductance. Mutual inductance is the ability of one inductor to to induce an EMF across another inductor placed very close to it. So what is mutual inductance? It is basically the ability of an inductor to induce an EMF across another inductor placed very close to it. When two coils are placed very close to each other, the magnetic flux caused by current in one coil links with the other coil and induces some voltage in the second coil. And this phenomenon is known as mutual inductance. So what is mutual inductance? When two coils are very close to each other, the magnetic flux caused by the current in one coil links the other coil and induces some voltage in the second coil. And that phenomenon is known as mutual inductance. And basically this phenomenon is transformer action. Depending on this phenomenon, the transformer is actually working. So suppose two coils are placed near each other, and as per the theory I have said, this is the diagram. Two coils are adjacent with each other, and in coil 1 current is flowing. Due to that, flux linkages are created, and this flux will link the nearby coil 2, and the EMF will be induced in the nearby coil. So let us consider as per this diagram. The first coil has N1 turns and carries a current I1, which gives rise to a magnetic field V1. Since the two coils are close to each other, some of the magnetic field lines through coil 1 will also pass through coil 2. Let F21 denote the magnetic flux through one turn of a coil 2 due to I1. Now, by varying I1 with time, there will be an induced EMF associated with the changing magnetic flux in the second coil. So what's happened? We have a coil with N1 turns. It carries a current of I1 and gives rise a magnetic field of V1. Since the two coils are just close to each other, whatever magnetic lines are created through coil 1 will also passes through coil 2 because they are just adjacent with each other. And let F21 denote the magnetic flux through one turn of coil 2 due to I1 current which is flowing in the first coil. Now by varying this I1 with time, there will be an induced EMF associated with the changing magnetic flux in the second coil. Now we will express these terms in mathematics. So that will be eta 21 equals to N2 d phi 21 by dt equals to d by dt of integration double integration d1 d2. And the rate of change of magnetic flux F21 in coil 2 is proportional to the time rate of change of the current in coil 1, and thus the voltage can be written as E21 equals to N2 d phi 21 by dt, and that is equals to N2 equals to d phi 21 by di1 into di1 into dt, that is M21 into di1 dt. Basically M21 is the mutual inductance, and it is represented as N2 is the number of turns of the second coil, and phi 2 is phi 21, definitely the flux linked by second coil, and this one represents the first coil divided by the current of the first coil. Similar way, if we want to represent the mutual induction of the first coil, then it will be just M12, and the value will be N1 phi 12 divided by I2 because it is created because of the I2 current, and that is the basic representation of mutual inductance. Now the mutual inductance M21 depends only on geometrical properties of the two coils, such as the number of turns and the radius of the two coils. In a similar manner, suppose instead there is a current I2 in the second coil and it is varying with time, and then the induced EMF in coil 1 becomes same way we will represent the mutual inductance of the second coil, and that will be M21 di1 dt. That means M12 is basically N1 phi12 divided by I2. Another mutual inductance. That means actually from reciprocity theorem we can say that this mutual inductance, that the effect of mutual inductance due to coil 1 to coil 2 or the coil 2 effect to coil 1 are just equal, and that proof we have done here. That is M12 is equals to M21, and that is the mutual inductance, the effect of one coil with another. Whatever effect I will create in the second coil, same effect second coil will give to first coil. So you have to remember that the mutual inductance of first coil to second coil, definitely as the effect is in the second coil, so the value will be M21. Which one is affected? 2. So the value of 2 will be first. So it will be M21, and the number of turns it will be N2 because it will link the second coil. So it is N2, and flux will be phi21 divided by which, for which current it is created? It is created because of I1. So divided by I1. Similar way, it will be just opposite for coil 2. So let us take an example, simple example. The combined inductance of two coils connected in series is 0.6 Henry and 0.1 Henry, depending on the relative directions of the current in the coils. If one of the coils, when isolated, has a self-inductance of 0.2 Henry, calculate the mutual inductance and coefficient of coupling. Basically, here we have used some formulas. Those formulas you have already studied in your basic electrical topic in first year. So we have just directly taken the formula for calculating these values. So let us consider our solution. The combined inductance of two coils connected in series, depending on the relative direction of the current in the coils, is given. It is known that the combined inductance in series, adding the condition is more than that in series opposing condition. So if the self-inductance L1 and L2 and mutual inductance is M, then we can write that when these two inductive coils are just placed in series, then what will be their effect? Definitely it will be L1 plus N2 plus 2M. Definitely this one is mutual inductance, and that will be equal to 0.6. And when they are just, the direction of current is just opposite, then it will be L1 plus L2 minus 2M equals to 0.1. And using these two equations and putting the value that L1 is 0.2 because self-inductance 0.2 Henry is given. So putting these values, we have got that the value of L2, the self-inductance of coil is 0.15 Henry and mutual inductance is 0.125 Henry. And the formula of coefficient of coupling, that is K equals to M divided by root over L1 L2. M value we have calculated 0.125. L1 value is given, that is 0.2, and L2 value we have calculated, that is 0.15, and putting all this value we have got the value of coefficient of coupling, and that value is 7.721. So this is our required answer. Related to this chapter, there are several numerical problems. In my next lecture, we will again do the calculations related to mutual inductance and coupling calculations, dot conventional, and whatever effect of dot convention series. Those part we will discuss in our next lectures. And the several numerical problems related to magnetic coupling we will tell in my next lecture series of magnetic coupled circuit. So thank you all. Thank you all for listening my lecture. And this topic I have covered from H. Chakraborty's book of circuit theory, and you can follow that book for understanding the chapter of magnetic coupling. Thank you. Thank you all for listening my lecture.